Okay, we are discussing chemical equilibrium, right? In that, some expressions we discussed. For example, if reaction 2 is equal to reverse of reaction 1. So what is the relation between corresponding equilibrium constants? And okay, the relation is K2 is equal to 1 by K1, or K1 is equal to 1 by K2. Next, if reaction 2 is equal to n into reaction 1, then K2 is equal to what we have? K1 power n. If reaction 1 plus reaction 2 gives third reaction, then K3 is equal to K1 into K2. If reaction 1 minus reaction 2 gives third reaction, then K3 is equal to K1 by K2. Okay. If N1 into reaction 1 plus N2 into reaction 2 gives third reaction, then we have K3 is equal to K1 power N1 plus into K2 power N2. N1 into reaction 1 plus N2 into reaction 2 gives reaction 3. Okay, so these are the various expressions we have. And what is the expression for equilibrium constant? Equilibrium constant is equal to forward rate constant by backward rate constant. Forward rate constant by backward rate constant, product side concentrations by reactant side concentrations. The powers are nothing but stoichiometric coefficients present in the balanced equation. Okay. If you write with respect to concentration, we indicate as Kc. With respect to pressures, we indicate as Kp. What is the relation between Kp and Kc? Kp is equal to Kc into RT whole power delta n, where delta n is product side number gaseous substance, number of moles of gaseous substance, minus reactant side number of moles of gaseous substance. Right? These are the some equations we discussed. Right? And what is the importance of equilibrium constant? That also we discussed. What is the importance of equilibrium constant? If equilibrium constant value is high, that indicates whether products are dominating or reactants are dominating. Products are dominating over reactants. And how to get the direction of equilibrium, the direction of reaction, whether it proceeds in the forward direction or backward direction, or the reaction is at equilibrium. How to verify? And right, by comparing equilibrium constant with the reaction coefficient. If reaction coefficient value is high, equilibrium proceeds in which direction? Backward direction. If if reaction coefficient value is small compared to K, Q is less than K, then it proceeds in forward direction. And if Q is equal to K, reaction is said to be at equilibrium. Okay. And you may add this point also. What is the relation between delta G naught and K? And that we discussed in thermodynamics. What is the relation between delta G naught and K? Minus RT ln K, right? Where K is called equilibrium constant. Okay, R minus 2.303 RT ln K, and delta G naught we can write as delta H naught minus T delta S naught also. So based on ln K versus 1 by 2, we can calculate delta H naught and delta S naught that we discussed in thermodynamics. And okay, right? This is the relation we have between delta G naught and equilibrium constant. Delta G naught is equal to minus RT ln K. Okay, I'm going to next concept and important factors affecting equilibrium. Factors affecting equilibrium, Le Chatelier's principle. Factors affecting equilibrium, Le Chatelier's principle. Okay. So in the beginning we discussed which information we can get from chemical equilibrium. Okay. So what are the various conditions we have to follow to get more yield of desired product? Okay. So what is the effect of pressure or concentration or temperature on equilibrium that we can study based on, okay, Le Chatelier's principle. And so whether we have to follow high pressure or low pressure to get more yield of desired product. Okay, we have to follow high temperature or low temperature. Okay, such conditions we can get by using what? Le Chatelier's principle. So first of all, what is Le Chatelier's principle? So according to Le Chatelier's principle, if equilibrium is subjected to stress, if equilibrium is subjected to stress, okay, it proceeds in the direction, you write, if equilibrium is subjected to stress, it proceeds in the direction, where stress decreases. According to Le Chatelier's principle, if equilibrium is subjected to stress, it proceeds in the direction where stress decreases. For example, we are increasing the concentration, then equilibrium proceeds in the direction where concentration decreases. Concentration decreases. Okay. For example, we are increasing the pressure. Equilibrium proceeds in the direction where pressure decreases. If we are increasing the temperature, equilibrium proceeds in the direction where temperature decreases. Okay. Simple concept. And right. So based on Le Chatelier principle, we can explain what is the effect of concentration, pressure, temperature, and addition of inert gas. Addition of inert gas. In this we have two conditions: at constant pressure and constant volume on equilibrium. Okay, based on Le Chatelier principles, what we can explain, and based on this principle we can explain the effect of concentration, pressure, temperature, and addition of inert gas at constant pressure as well as constant volume on equilibrium. So what is the effect of these on equilibrium that we have to see? And so what is the effect of concentration, pressure, temperature, and addition of inert gas at constant pressure as well as at constant volume on equilibrium that we can explain based on Le Chatelier principle. And so in that first one, concentration. So effect of concentration on equilibrium. And effect of concentration on equilibrium. Okay, for example, I am taking a reaction like this under equilibrium. Okay, consider a reaction under equilibrium. Reactants are in equilibrium with the products, right? Now, for example, we are increasing the concentration of reactants. On increasing the concentration of reactants, reaction proceed in the direction where concentration of reactants decreases. Okay, that means forward direction or backward direction? Forward direction. In the forward direction, concentration of reactants decreases. So if you increase the concentration of reactants, equilibrium proceeds in forward direction, or equilibrium proceeds towards reactants or towards products. And equilibrium proceeds towards products, or equilibrium proceeds right side or left side. And equilibrium proceeds right side. So if you increase the concentration of reactants, equilibrium proceeds in forward direction or towards products or towards right side. If you decrease the concentration of product, what happens? If you decrease the concentration of product, okay, whatever the product formed, immediately you are collecting the product. As fast as product formed, we are collecting the product, and then what happens? It proceeds in which direction again? Forward direction only. We are decreasing the concentration of product means it shifts in the direction where concentration of product increases. That means again forward direction only. So concentration of reactant you may increase, or concentration of product you may decrease. So if you want to get more yield of product, okay, what you have to do only? You may increase either concentration of reactant, or you may collect as fast as the product formed only. Then you may get more yield of product. Okay. Next one. If you increase the concentration of product, or what? If you decrease the concentration of reactant, on increasing the concentration of product or on decreasing the concentration of reactant, what happens? And equilibrium proceeds in which direction? Backward direction, right? Equilibrium proceeds in backward direction, or towards reactants or towards products, and towards reactants, or left side or right side, and left side. On increasing the concentration of product or decreasing the concentration of reactant, equilibrium proceeds in backward direction or towards reactants or left side. So whenever we are changing the concentration, what about equilibrium constant value? Changes or doesn't change? Equilibrium constant depends on what? We discussed in thermodynamics. Equilibrium constant depends on what? Temperature. Equilibrium constant depends only on temperature. So whenever we are changing the concentration of either reactant or product, only direction of equilibrium changes. Whether it may proceed in forward direction or backward direction, only the direction of equilibrium is affected, but equilibrium constant value is not affected. And that I will explain by an example. Okay. Initially, we started with 100 reactant molecules, and for example, initially we started with what? 100 reactant molecules, number of moles initially, and at equilibrium, let us consider 40 are converted to product, and so remaining 60 as reactants only. Okay, remaining concentration of reactant is 60, concentration of product is formed is 40, and so equilibrium constant means what? Product concentration by reactant concentration. So 40 by 60. So we are getting 4 by 6. That means 2 by 3 we are getting. Okay. Now, for example, to this equilibrium, already it is at equilibrium. At equilibrium 60 molecules of reactant we have, 40 molecules of product we have, 60 molecules of reactant and 40 molecules of product we have. To this I am adding again 100 reactant molecules. I am adding again 100 reactant molecules. Now it proceeds in which direction? Forward direction. Okay, we are increasing the concentration of reactant, so it proceeds in which direction? Forward direction. So such that again this equilibrium is disturbed. Okay, it proceeds in the forward direction and finally it reaches what? Equilibrium. So that is again new equilibrium is arrived. Okay, new equilibrium is arrived. Since this proceeds in which direction? Forward direction. It proceeds in forward direction up to appearance of new equilibrium. Up to appearance of new equilibrium. At new equilibrium, what about the reactant molecules and product molecules? If you see, it is 120 and 80, and again we are adding 100 molecules. In that 40 converted to product, the remaining 60 as reactant molecules, and so 120, 80, and so therefore now equilibrium constant is product concentrations by reactants concentrations. So 42s are 43s are 2 by 3. Now is there any change in the equilibrium constant value or no change? No change in the equilibrium constant value, but what happens to direction of equilibrium? changed. So only direction of equilibrium changes, but equilibrium constant is not affected by changing the concentration. K depends only on what? Temperature. Okay, right? First you write this example. Later we will see problems also based on this concept. So in your real life also you have to follow Le-Chatelier principle, right? If you feel stress, you have to move in the direction where stress decreases. Okay, you have to balance your stress, always maintain equilibrium, right? Okay, write that point. So therefore by changing concentration, by changing concentration, by changing concentration, only direction of equilibrium, only direction of equilibrium is affected. By changing concentration, only direction of equilibrium is affected, but no change in, but no change in, but no change in equilibrium constant value, but no change in equilibrium constant value. By changing concentration, only direction of equilibrium is affected, but no change in equilibrium constant value. Okay, right? This is the first factor. Okay, that affecting equilibrium. So the next one, pressure and effect of pressure on equilibrium. What is the effect of pressure on equilibrium? Next put heading, effect of pressure on equilibrium. So based on Le-Chatelier principle, sometimes simple questions and 4 marks questions given previously. Okay, right? Effect of pressure on equilibrium. We know pressure is directly proportional to number of moles of gas or not. As number of moles of gas increases, pressure also increases. PV is equal to nRT we have. PV is equal to nRT. Pressure is directly proportional to number of moles. So therefore, we can explain the pressure of effect of pressure based on number of moles. We can explain the effect of pressure based on number of moles. For example, we are increasing the pressure, then equilibrium shifts in the direction where pressure decreases. Where pressure decreases, that means where number of moles decreases. Okay, while we are increasing the pressure, equilibrium proceeds in the direction where pressure decreases or where number of moles decreases. Next, if you decrease pressure, what happens? Equilibrium shifts in the direction where pressure increases. Where pressure increases means where number of moles increases. Or we can explain the effect of pressure by volume also. While we are increasing the pressure, what happens to volume? Decreases. So on increasing pressure, equilibrium proceeds in the direction where volume decreases. Okay, write that point. So we know pressure is directly proportional to number of moles. Right, on increasing pressure, equilibrium proceeds. On increasing pressure, equilibrium proceeds in the direction. Equilibrium proceeds in the direction where pressure decreases. On increasing the pressure, equilibrium proceeds in the direction where pressure decreases, or number of moles decreases or volume decreases. equilibrium shifts in the direction where pressure decreases or number of moles decreases or volume decreases. Next, if you write on decreasing pressure, then what happens? Equilibrium proceeds in the direction where pressure increases or number of moles increases or volume increases. On decreasing pressure, equilibrium proceeds in the direction where pressure increases or number of moles increases or volume increases. If you decrease pressure, what happens to volume? Increases. Pressure is inversely proportional to volume. Okay, if you see the example, for example, N2 gas plus 3H2 gas, we are preparing ammonia from nitrogen and hydrogen gas. Haber's process, if you follow Haber's process. Okay, high pressure is favored or low pressure is favored for the formation of ammonia. Okay, if you see that, which pressure is favored, and if you increase the pressure, it proceeds in forward. Consider equilibrium, and if you increase the pressure, it proceeds in forward direction, or if you decrease the pressure, it proceeds in forward direction. On increasing pressure, it proceeds in forward direction. Here, if you see on increasing pressure, what happens? Equilibrium proceeds towards what? Less number of moles. Equilibrium proceeds towards less number of moles. Towards product, we have less number of moles, or towards reactant, less number of moles we have. Towards product, we have less number of moles. Towards reactants, 4 moles of gaseous substance we have. Towards product, we have only 2 moles of gaseous substance we have. So on increasing pressure, equilibrium proceeds in which direction? Forward direction. That means whether high pressure is favorable or low pressure is favorable for formation of ammonia. High pressure is favorable for formation of ammonia. Okay. Next, if you decrease pressure, on decreasing pressure, equilibrium proceeds in which direction? Backward direction. Equilibrium proceeds in backward direction. For example, if you take decomposition of PCl5 gas to give PCl3 gas plus Cl2 gas. Now, if you increase pressure, it proceeds in which direction? Backward direction. Okay, on increasing pressure, equilibrium proceeds where number of moles decreases. It proceeds towards less number of moles. So therefore, on increasing pressure, it shifts in which direction? Backward direction. On decreasing pressure, it proceeds in forward direction. Okay, and here delta n is positive or negative, and negative. If delta n is negative, it proceeds in forward direction. Number of moles of gaseous substance decreasing. Here delta n is positive. Number of moles of gaseous substance towards product side minus number of moles of gaseous substance towards reactant side. 2 minus 1, positive 1. Here 2 minus 4, minus 2 we are getting. 2 minus 4, minus 2. Finally, if you take decomposition of hydrogen iodide gas to give H2 gas plus I2 gas, what about delta n for this? 2 minus 2, 0. Okay, that means what about the effect of pressure? On this equilibrium, no effect of pressure. On this equilibrium, no effect of pressure. Towards reactant side and product side, we have same number of moles of gaseous substance. So no effect of pressure. Okay. Next, even by changing pressure, whether equilibrium constant value changes or doesn't change. Doesn't change, since equilibrium constant depends only on temperature. Here also the direction changes such that no change in the concentrations. Okay, concentrations changes, but equilibrium constant cannot be changed. Previously concentration is changed or not? Equilibrium concentrations are initially what? 60-40, but after new equilibrium concentrations are what? 120-80. Concentrations are changed, but equilibrium constant cannot be changed. So concentrations are changed such that no change in the equilibrium constant value. Like that, concentrations will be changed. Okay. So next one, effect of temperature on equilibrium. Effect of temperature on equilibrium. Right. By changing concentration and pressure, by changing concentration and pressure, only the direction of equilibrium, only the direction of equilibrium is affected, only the direction of equilibrium is affected, but no change in equilibrium constant value. By changing concentration and pressure, only the direction of equilibrium is affected, but no change in equilibrium constant value. But by changing temperature, both direction of equilibrium and K value, equilibrium constant value, are affected. But by changing temperature, both direction of equilibrium and equilibrium constant value are affected. Both will be changed. Both will be changed. What is the effect of temperature on equilibrium constant? That we explained by an equation. What is that equation? We discussed in thermodynamics. What is the name of that equation? Kirchhoff equation gives relation between delta H and T, K and T. That is Van 't Hoff equation we discussed. Okay. I told you in the beginning you will get more time, so you have to revise as many times as possible. Otherwise, it is very difficult to cover at the ending. Okay, unlimited syllabus we have, right? Van 't Hoff equation gives relation between K and T. What is that relation we have? Ln K is equal to delta H naught by RT square into dt. D by dt of ln K. This is differential form we have. Delta H naught by RT square. Integral form is ln K2 by K1 is equal to delta H naught by R into T2 minus T1 by T1 T2. Okay. This is the integral form of Van 't Hoff equation we have. So from this, if you increase the temperature, we are increasing the temperature means T2 greater than T1. So this bracket term is positive. Okay, if you take endothermic reaction means delta H naught positive. Okay, that means K2 greater than K1 we will get. That means as temperature increases, K also increases. For which reaction? Endothermic reaction. Right side we are getting positive. For exothermic reaction, delta H naught negative. We are getting negative means K2 is less than K1. K2 is less than K1. That means as temperature increases, K value decreases. As temperature increases, K value decreases. Okay, all these we discussed at thermodynamics. Okay, if you take endothermic reaction, for endothermic reaction, that is reactant plus heat gives rise to product. Endothermic reaction means delta H naught positive or negative? Positive. So as temperature increases, what about K value? Also increases. As temperature increases, K value increases. Next, as temperature increases, equilibrium proceeds in which direction? As temperature increases, equilibrium proceeds in which direction? Forward direction. We are increasing the temperature means we are providing what? Heat energy. We are supplying heat energy. So it proceeds in the direction where heat energy is consumed. Where heat energy is consumed. In the forward direction, heat energy is consumed. In the backward direction. In the forward direction, heat energy is consumed. So it proceeds in which direction? Forward direction. If you take endothermic reaction, as temperature increases, it proceeds in forward direction. As temperature decreases, it proceeds in which direction? Backward direction. As temperature decreases, it proceeds in backward direction. That's why K value increases. And if K value is high, products dominates or reactants dominate? Products dominate. Okay, so as temperature increasing, what? K value increases. Since products, it proceeds in which direction? Forward direction. Products concentration is increasing. Okay, next one. If you take for exothermic reaction, delta H naught negative. So reactant gives rise to product plus heat. Now for this, as temperature increases, what about equilibrium constant value? Decreases. From this equation we can explain. Right side we are getting negative. Negative means K2 is less than K1. As temperature increases, K value decreases. Next, as temperature increases, equilibrium proceeds in which direction? Backward direction. It proceeds in the direction where heat energy is consumed, that is backward direction. Or if you decrease temperature, it proceeds in which direction? Forward direction. If you decrease temperature, it proceeds in forward direction. So by changing temperature, not only direction affected, but equilibrium constant value also affected. K is function of what? Temperature only. K is function of temperature only, that we discussed based on Van 't Hoff equation. Okay. For example, at 40 degrees centigrade, K value for a given reaction is 50 units a day at 40 degrees centigrade. Now if you observe at 50 degrees centigrade, K value changed to 60 units. Now tell me what is the nature of reaction, whether it is what is the nature of reaction, whether it is endothermic or exothermic. And endothermic, since as temperature increases, K also increased. Okay, so what about nature of reaction? And nature of reaction is what? Endothermic. Nature of reaction means whether it is endothermic or exothermic. Okay. As temperature increases, it proceeds in which direction? Forward direction. For example, at 30 degrees centigrade, K value is 60 units. At 40 degrees centigrade, K value is 45 units. Now what about the nature of reaction? Nature of reaction is exothermic. As temperature increases, K value is decreasing. So it is exothermic. It is exothermic. So this is the effect of temperature on equilibrium. Next we have to see what? Addition of inert gas. Two cases we have, at constant volume and at constant pressure. Okay. Next put heading addition of inert gas. Addition of inert gas. Two cases. One is at constant volume. Constant volume means with movable piston or immovable piston, and we have to take immovable piston. Okay, closed vessel we have to take. Okay, so we have a reaction under equilibrium like this. We have a reaction under equilibrium like this. Okay, to this we are adding inert gas at constant volume. Okay, constant volume, non-expanding chamber, with immovable piston we are taking. Okay, reactants pressure to this we are adding some inert gas, and we are adding some inert gas. Now what is the effect on equilibrium, whether equilibrium is affected or not, and what about that effect, whether it proceeds in forward direction or backward direction. If you see, okay, this is inert gas, and inert gas means it participates in the reaction with either reactants or products, or it doesn't involve in the reaction. It doesn't involve in the reaction. So it doesn't involve in the reaction means, is there any change in the number of moles of reactants and products, or no change in the number of moles of reactants and products? No change in the number of moles of reactants and products. Is there any change in the volume, or no change in the volume? No change in the volume. We are adding at constant volume. So concentration, if you take, concentration is equal to what? Number of moles by volume in liters. Number of moles by volume in liters. So number of moles are not changing, constant. Volume is also constant. That means there is no change in the either concentration of reactants or concentration of products. That means if you add inert gas at constant volume, whether that equilibrium is affected or not affected. That equilibrium is not affected, since no change in the number of moles of reactants or number of moles of products. Since ideal gas, inert gas we are taking, inert gas doesn't react with either reactants or products. Okay, right? We are adding inert gas at constant volume. Right? By addition of inert gas, at constant volume, by addition of inert gas at constant volume, no change in number of moles of either reactants or products. No change in number of moles of either reactants or products, and hence no change in concentrations of either reactants or products, and hence no change in concentrations of either reactants or products. Okay, so equilibrium is not affected by addition of inert gas at constant volume. So equilibrium is not affected by addition of inert gas at constant volume. So equilibrium is not affected. Finally, you write, so equilibrium is not affected by addition of inert gas at constant volume. Okay, so we are adding inert gas, so no change in the number of moles of either reactants or products, since they do not involve in the reaction. So number of moles constant, we are adding at constant, volume also constant, so therefore concentration of reactants and products also remains constant. So equilibrium is not affected. So whatever may be the type of reaction, means, for example, I am taking a reaction like this: N2 gas plus 3H2 gas, 2 moles of ammonia gas. Okay, we are adding what? Inert gas at constant volume. We are adding inert gas at constant volume. What about the type of reaction? What about delta N for this reaction? Positive or negative? Negative. 2 minus 4 minus 2. That means negative. 2 minus 4 minus 2, that means negative. So whatever may be the type of reaction you take, whether delta n positive or negative or 0, so no change in the number of moles of reactants and products, so no effect on equilibrium, no effect on equilibrium. So whatever may be the type of reaction you consider. For example, if you take decomposition of PCl5 to give PCl3 gas plus Cl2 gas, we are adding inert gas at constant volume. We are adding inert gas at constant volume. Now what is the effect on this equilibrium? Okay, if there is constant volume, immediately you go to no effect on equilibrium. Immediately you go to that option, no effect on equilibrium. What about delta n value? Positive. 2 minus 1, that is 1 positive. If you take decomposition of hydrogen iodide gas, so here we are adding inert gas at constant volume. What about delta n for this reaction? 0. Okay, no effect on equilibrium. So whatever may be the type of reaction, if you add inert gas at constant volume, there is no effect on equilibrium. Okay, so next one, second case, constant pressure. Next one, constant pressure. Constant pressure means we have to take with movable piston or immovable piston. Movable piston. Okay, for example, here some piston we are taking movable piston. Same reactants under equilibrium. To this, what we are adding? We are adding inert gas at constant pressure. Okay, so whenever we are adding inert gas to this, pressure increases or not? As we are adding inert gas, pressure increases, but it has to maintain what? Constant pressure. To maintain constant pressure, what happens? Volume increases. Okay, whenever we are adding inert gas, pressure increases. To decrease pressure, to maintain constant pressure, it undergoes what? Expansion. Volume increases. Okay, while we are adding inert gas, what happens? It undergoes expansion. Volume increases. Okay. Okay, on adding inert gas at constant pressure, what happens? Volume increases as we are taking movable piston. Okay, now is there any change in the number of moles of reactant and product, or no change in the number of moles of reactant and product? No change in the number of moles of reactant and product, since whether they involve in the reaction with inert gas or they do not involve in the reaction. They do not involve in the reaction, okay, with the inert gas. So no change in the number of moles of reactants or products, but volume is increased. Volume is increased, so therefore number of moles per unit volume increases or decreases? Decreases. Number of moles of reactant or product per unit volume decreases. Okay, right? Previously in 1 liter 100 moles are there. In 1 liter 100 moles are there. Now it is undergoing expansion. In 2 liters same 100 moles are there. In 2 liters same 100 moles are there. Number of moles are not changing, but number of moles per unit volume decreases. And so therefore equilibrium shifts in the direction where number of moles increases. Equilibrium shifts in the direction where number of moles increases. This is opposite to pressure and opposite to pressure. In the case of pressure, on increasing pressure, equilibrium shifts in the direction where number of moles decreases. But if you add inert gas at constant pressure, equilibrium proceeds in the direction where number of moles increases. And right? On addition of inert gas, at constant pressure, on addition of inert gas at constant pressure, comma, no change in number of moles of either reactants, or products, but volume increases. So number of moles of reactants and products, per unit volume, decreases. And hence equilibrium shifts in the direction, where number of moles increases. Okay. Now I am taking the same 3 reactions, and previously we considered 3 reactions. The same 3 reactions I am taking. 2 moles of N2 gas plus 3 moles of H2 gas, 2 moles of NH3 gas. Tell me what is the effect of addition of inert gas at constant pressure? It proceeds in which direction, Andy? Backward direction, where number of moles are increasing, Andy? In the backward direction number of moles are increasing. So it proceeds in backward direction. Delta N positive or negative for this reaction? Negative. Okay. So it proceeds in which direction, Andy? Backward direction. So it proceeds in the direction where number of moles increases. So what about this? We are adding inert gas at constant pressure. For this delta N is positive. So it proceeds in which direction? Forward direction. And lastly, decomposition of hydrogen iodide. Delta N value 0. We are adding inert gas at constant pressure. Here delta N is 0, therefore no effect on equilibrium. No effect on equilibrium. Same number of moles we have towards reactants and the product side. So no effect on equilibrium. So this is reverse to effect of pressure, and you remember in the case of pressure it proceeds in the direction where number of moles decreases. In the case of addition of inert gas at constant pressure, it proceeds in the direction where number of moles increases. Next we see what is the effect of catalyst on equilibrium andi. Lastly, I will give you all the conclusions and what are the points we have to remember. All those conclusions I will give you from Le Chatelier principle. Okay. Next, what is the effect of catalyst on equilibrium andi? So this is some reaction I am taking under equilibrium. Okay. If you do the same reaction by using catalyst, what happens? If you use catalyst, what happens? Rate of reaction increases. Rate of reaction increases since activation energy required for the reaction decreases. This question given in 2-3 competitive exams. By using catalyst, what happens? By using catalyst, what happens? Rate of reaction increases. Why rate of reaction increases? Activation energy required for the reaction decreases. Activation energy is the minimum energy, minimum additional energy that we have to provide to reactants to proceed in the forward direction, or that is the minimum additional energy we have to provide to products to proceed in the backward direction. So if you see the energy profile diagram, for example, we have like this. This is the energy of reactants, this is the energy of products. This is energy of reactants ER. If you do at constant pressure, that is written as what? H and enthalpy of reactants. This is enthalpy of products or energy of reactants, energy of products. Okay, let us consider this is energy profile diagram we are getting without catalyst. This is energy profile diagram we are getting without catalyst. Okay, so if you see without catalyst, what is the activation energy required for forward reaction? This is the activation energy required for forward reaction. Okay, to convert reactant to product, reactants have to overcome this energy barrier. Reactants have to overcome this energy barrier. To overcome this energy barrier, what is the additional energy required? We have to supply. That is called what? Activation energy. So this is the activation energy for forward reaction. EAF, activation energy for forward reaction. And what is the activation energy for backward reaction? This is the activation energy for backward reaction. Okay, this is without catalyst. Now if you use catalyst, what happens? Reaction proceeds by some new path. Reaction proceeds by some new path where activation energy required for forward reaction as well as backward reaction decreases. Now what is the activation energy required? Now this is the activation energy required EA dash I am indicating for forward reaction. And what is the activation energy required for backward reaction? This is the activation energy required for backward reaction. So this is what with the catalyst. So this is the difference. Okay, so while we are using catalyst, what happens? Reaction proceeds by a new path where the activation energy required for only forward reaction decreases, or the activation energy required for both forward and backward reaction decreases. The activation energy required for both forward and backward reaction decreases. Okay, this is EAF. Next EAB in the absence of catalyst, EA-F, EA-B in the presence of catalyst. You write first of all this energy profile diagram. What is the change in enthalpy during the reaction? This is what? Change in enthalpy during the reaction. Enthalpy of products minus enthalpy of reactants. Enthalpy of products minus enthalpy of reactants. You write this one, otherwise you write here HR. This is HR. This is what? HP, enthalpy of products. Okay, this is enthalpy of products, enthalpy of reactants, EAF, A dash F, A B, A dash B. Activation energy for forward and backward reactions with catalyst and without catalyst. And this is the change in energy during the reaction. Whatever may be the path you follow, whether enthalpy of reactants and products changes or doesn't change. Whatever the path you follow, enthalpy of reactants and products doesn't change. Hess law we discussed, delta H, heat of reaction remains same. Here we are following two paths. One is with catalyst, another one is without catalyst. We are following two paths, but delta H changes or doesn't change. Delta H doesn't change. In both the paths, energy of reactants and products same. Delta H also same. Hess law we discussed. Right? By using catalyst, reaction proceeds by a new path, where activation energy required for both forward reaction and backward reaction decreases. Activation energy required for both forward reaction and backward reaction decreases. So rate of both forward and backward reactions. Increases. So rate of both forward and backward reactions increases. And hence the time required to reach equilibrium decreases. Now tell me whether is there any change in the equilibrium concentrations of reactants and products, or no change in the equilibrium concentrations of reactants and products. No change in the equilibrium concentrations of reactants and products. Only what happens? The time required to reach the equilibrium decreases, but no change in the equilibrium concentrations of reactants and products. That means, is there any change in the K value or no change in the K value? No change in the K value. K changes only with temperature. So by using catalyst also K doesn't change. Write that point. Okay. Equilibrium is reached in less time, but no change in equilibrium concentrations of reactants and products. And hence no change in K value. So finally, if you use catalyst, what happens? Activation energy changes. Next, rate of reaction changes. Rate of forward reaction and backward reaction changes. That means rate constant for forward reaction, rate constant for backward reaction changes. Next, time required to reach equilibrium changes. Time required to reach equilibrium changes. All these changes are observed by using catalyst. By using catalyst, what are the changes we observe? Activation energy changes for both forward and backward reaction. EAF and EAB. EAF changes, EAB changes, rate of forward and backward reaction changes. That means rate constant for forward reaction changes, rate constant for backward reaction changes, time required to reach equilibrium changes. But what are which values doesn't change and by using catalyst? Equilibrium concentrations of reactants and products doesn't change. Next, equilibrium constant value, K value, doesn't change. What about enthalpy of reactant? Changes or doesn't change? Doesn't change. Enthalpy of products doesn't change. Change in enthalpy, same. So by using catalyst, equilibrium concentrations of reactants and products, K value, enthalpy of reactants, enthalpy of products, delta H, okay, all this doesn't change. Right. Just you remember this final conclusion. How rate of reaction changes or rate constant changes by using catalyst, that we'll see in chemical kinetics and again. Okay. What is the relation between rate with catalyst and without catalyst? What is the relation between rate constants with catalyst and without catalyst, that we'll see in chemical kinetics. Okay, so based on Le-Chatelier principle, we can explain what is the effect of pressure on melting point of ice and what is the effect of pressure on melting point of ice. So we are taking a physical process, and here melting of ice is a physical process or chemical process and physical process. So by Le-Chatelier principle we can explain what? Both physical process and chemical process. And effect of pressure on melting point of ice. So if you take ice is in equilibrium with water, and whether ice occupies more volume or water occupies more volume, ice occupies more volume. The density of ice is small compared to water. That's why ice floats over water. Ice occupies more volume, water occupies less volume. Now we know on increasing pressure, equilibrium shifts in the direction where volume increases or decreases, and volume decreases. If you increase the pressure, what happens to volume? Decreases. That means this equilibrium shifts in which direction, and equilibrium proceeds in backward direction or forward direction, and forward direction, right? On increasing pressure, equilibrium proceeds in forward direction. Forward direction means whether it favors melting of ice or it opposing melting of ice. It favors melting of ice. Ice is converting to water. It favors melting of ice, and that means if you increase the pressure, what happens to melting point of ice, and increases or decreases, and decreases, since it favors melting of ice. Once if you apply pressure on ice, what happens, and it easily melts or not? If you apply pressure on ice, what happens? It easily melts. That means its melting point is increasing or decreasing, and decreasing, and okay, right? On increasing pressure, equilibrium proceeds in forward direction. Therefore on increasing pressure, melting point of ice decreases. On increasing pressure, melting point of ice decreases. On increasing pressure, melting point of ice decreases. Next, if you see what is the effect of pressure on boiling point of water. Effect of pressure on boiling point of water. Effect of pressure on boiling point of water. So now At boiling point we know water is in equilibrium with the water vapor. At equilibrium water is in at boiling point water is in equilibrium with water vapor. Which one occupies more volume andi? Water vapor occupies more volume. Water occupies less volume. Water vapor occupies more volume. Now if you increase pressure, equilibrium proceeds in which direction andi? Backward direction. Okay, on increasing pressure volume decreases, so it proceeds in backward direction. Backward direction means whether it favors boiling of water or opposes boiling of water. Opposing boiling of water. Okay, it opposing boiling of water. That means still we have to supply more heat energy, and still we have to supply more heat energy to overcome this factor. To overcome this factor. That means whether boiling point of water increases or decreases, and boiling point of water increases, and okay, 1 atmospheric pressure. At 1 atmospheric pressure, what is the boiling point of water? 100 degrees centigrade. If you take, for example, above 1 atmosphere, what is the boiling point of water? We will get above 100 degrees centigrade. Okay. So therefore, on increasing pressure, what happens to boiling point of water? Increases. Boiling point of water increases. So while we are increasing pressure, equilibrium proceeds in the backward direction. That means it opposes boiling of water. So to overcome that, still we have to supply more heat energy. That means boiling point of water increases. Next one, right? Effect of temperature on solubility of solid in liquid. Effect of temperature on solubility of solid in liquid. So this we will see in solutions topic, and in solutions topic we will get solubility concept. So effect of temperature on solubility of solid in liquid. For example, I am taking a solid substance. Okay, we are adding to a solid, to liquid. We are taking a solid substance, we are adding to a liquid, and we are getting what? Solution. Solid in liquid solution. We are getting some solution, and okay. For example, if it is endothermic, and if it is endothermic, heat is absorbed during this process. Now if you increase the temperature, it proceeds in which direction? Forward direction. On increasing temperature, that means we are supplying heat energy, it proceeds in the direction where heat energy is consumed, in the forward direction. It proceeds in the forward direction. Forward direction means whether solubility of solid is increasing or decreasing. Solid is separating from liquid, or solid is more amount of solid is dissolving in the liquid. More amount of solid is dissolving in the liquid. Okay, solution we are getting, right? Solid is not separating from the solution. So on increasing temperature, it proceeds in the forward direction. That means what happens to solubility of solid? Increases, and so solubility increases. Okay, so it depends on whether it is endothermic reaction or exothermic reaction. If you take exothermic reaction, solid plus liquid, we have solution plus heat energy. Now if you increase the temperature, it proceeds in which direction? Backward direction. Backward direction means solid is separating from the solution. Solid is separating from the solution. That means solubility is increasing or decreasing? Decreases. Solubility decreases. So they may mention you whether it is endothermic or exothermic. So if they mention whether it is endothermic or exothermic, based on that you may verify. If it is endothermic, if you decrease the temperature, solubility increases. If you increase the temperature, solubility increases. Exothermic. Okay, if you decrease the temperature, solubility decreases. If you increase the temperature, solubility decreases. Or if you decrease the temperature, what happens to solubility here? Increases. On decreasing the temperature, solubility increases. And you write, as temperature decreases, solubility increases in the second case. As temperature decreases, solubility increases. Next one, and one more application of Le-Chatelier principle. Effect of pressure on solubility of gas in liquid. Effect of pressure on solubility of gas in liquid. Effect of pressure on solubility of gas in liquid. So we are taking a gaseous substance, so we are dissolving in a liquid. We are taking a gaseous substance, we are dissolving in a liquid. So we will get what? Gas in liquid solution. Some solution we are getting in here. Okay, gas in liquid solution we are getting. Whether gas occupies more volume or gas in liquid occupies more volume. Whenever it is in the form of gas, it occupies more volume. Whenever it is dissolved in a liquid, what happens to its volume? Decreases. Okay, decreases. This is similar to condensation of gases. And this is considered as condensation of gases. And during condensation, heat energy is released or absorbed. Heat energy is released. When a gas is dissolved in a liquid, that is considered as what? Condensation of gas. During condensation, heat energy is released. During evaporation, heat energy is absorbed. Okay, so therefore, on increasing pressure, equilibrium proceeds in which direction? And equilibrium proceeds in forward direction. If you increase the pressure, it proceeds in the direction where volume decreases. Equilibrium proceeds in forward direction. Forward direction means whether more amount of gas is dissolved in liquid or gas is separating from solution. And more amount of gas is dissolved in the liquid. And so that means solubility increases. On increasing pressure, solubility increases. And if you increase temperature, what happens? And it is endothermic or exothermic? And exothermic. If you increase temperature, equilibrium proceeds in which direction? Backward direction. That means solubility decreases. I explained it, Henry's law. Aquatic species feel more comfortable in cold water or warm water. And aquatic species feel more comfortable in cold water. In warm water, if you increase the temperature, what happens to solubility of gases? Decreases. Dissolved oxygen decreases in water. If you increase the temperature, warm water if you take, okay, solubility of oxygen decreases, dissolved oxygen value decreases. Therefore, aquatic species cannot feel more comfortable in warm water. Okay, so on increasing temperature, solubility of gases decreases. Next, we can also explain common ion effect also. We can also explain common ion effect based on Le-Chatelier principle. Common ion effect. If you take silver chloride solid, if you dissolve in water, there exists an equilibrium between Ag plus and Cl minus ions and AgCl solid. Since it is a sparingly soluble salt, silver chloride is what? Sparingly soluble salt. Sparingly soluble salt means its solubility is very, very low. And okay, its solubility is very, very low. For example, we are adding 100 AgCl molecules to water. In that only 2 are soluble and the remaining 98 precipitated. And the remaining 98 precipitated. So whatever the 2 molecules soluble, those 2 molecules exist in the form of ions. And okay, this comes under ionic equilibrium. This we study in ionic equilibrium. Ions are involved here. Ions are involved here. This is set to be ionic equilibrium. So to this, okay, for example, we are adding an electrolyte, containing common ion. So you may add KCl. KCl contains a common ion or not? Yes, what is the common ion? Cl minus ions. Or you may add AgNO3. You may add AgNO3 salt. So what is the common ion in this case? Ag plus is the common ion. So whenever to this equilibrium, if you add an electrolyte containing common ion, that is either Ag plus or Cl minus, for example AgNO3 or KCl, then what happens? This equilibrium proceeds in which direction? Here we are increasing the concentration of products or reactants. Products. If concentration of products increases, equilibrium proceeds in which direction? Backward direction. Okay. So on addition of an electrolyte containing common ion, this equilibrium proceeds in backward direction. That means solubility still increases or decreases? Decreases. Already its solubility is low, still its solubility decreases. This we will discuss in electrochemistry. We will get in electrochemistry. We will discuss problems also based on this solubility concept. At electrochemistry we will discuss. Okay, in detail. This is called common ion effect. Okay. Similarly, if you take a weak electrolyte, acetic acid is a weak electrolyte or strong electrolyte? Weak electrolyte. Acetic acid is a weak electrolyte. So there exists an equilibrium between molecules, undissociated molecules, and ions. Okay. To this, if you add any strong electrolyte containing common ion, that is CH3COO Na I am adding. What is the common ion here? Acetate ion is the common ion, or I am adding HCl. What is the common ion here? H plus is the common ion. Okay. So in both the cases, equilibrium proceeds in which direction? Backward direction. Equilibrium proceeds in backward direction. Here also equilibrium proceeds in backward direction. As concentration of products increasing or reactants increasing? Concentrations of products increasing, so equilibrium proceeds in backward direction. Write the definition of common ion effect. The decrease in the solubility of sparingly soluble salt, the decrease in the solubility of sparingly soluble salt, the decrease in the solubility of sparingly soluble salt, the decrease in the solubility of sparingly soluble salt, or the decrease in the dissociation of weak electrolyte, the decrease in the dissociation of weak electrolyte, the decrease in the dissociation of weak electrolyte in the presence of strong electrolyte, containing common ion, in the presence of strong electrolyte containing common ion is called common ion effect, is called as common ion effect. So in both the cases what we are observing, and here what happens to solubility of silver chloride, increasing or decreasing, and backward direction means solubility of silver chloride decreases. Here it proceeds in the backward direction means dissociation of acetic acid is increasing or decreasing andi. Dissociation of acetic acid is decreasing andi. Okay, so that is called common ion effect. So these are some applications of Le Chatelier's principle. Okay, if you see, write the conclusions from Le Chatelier's principle and write the conclusions from Le Chatelier's principle. If you have a reaction like this, if you increase the concentration of reactant or if you decrease the concentration of product, it proceeds in which direction andi? Forward direction or backward direction andi? Forward direction. If you decrease the concentration of reactants or if you increase the concentration of products, it proceeds in which direction? Backward direction. If you increase pressure, it shifts towards less number of moles or more number of moles andi? Less number of moles. On increasing pressure, it proceeds towards less number of moles or less volume or more volume andi? Less volume. Less number of moles or less volume. Okay. If you decrease pressure, it proceeds towards what? More number of moles or more volume. Okay. Next, endothermic reaction. If you take endothermic reaction, as temperature increases, it proceeds in which direction andi? For endothermic reaction, forward direction, and as temperature increases, K value increases. As temperature increases, K value increases. Next, if you write for exothermic reaction andi, as temperature increases, it proceeds in which direction? Backward direction. K value decreases. Exothermic reaction andi. Next, if you see addition of inert gas, in this we have two cases, okay, that I am giving in the form of a table. Type of reaction at constant volume and at constant pressure. Type of reaction means delta N positive, delta N negative, delta N 0. At constant volume, whatever may be the type of reaction, is there any effect on equilibrium or no effect on equilibrium? No effect on equilibrium, whatever may be the type of reaction. At constant pressure, reverse, I told you, it is reverse to pressure, and if you increase pressure, less number of moles, but at constant pressure, more number of moles. And delta N positive means number of moles are increasing or decreasing? Increasing. Increasing means forward direction, towards more number of moles. Forward direction. Negative means backward direction. 0 means no effect. Catalyst, already I gave you catalyst conclusions, you write. What about catalyst? And rate of reaction changes, rate constant changes, time decreases, time changes, activation energy changes, but which do not change. And enthalpy of reactants, products, change in enthalpy, equilibrium concentrations of reactants and products, K value doesn't change. Okay, those you write it. Already I gave conclusions for catalyst. You write those conclusions. If you increase the temperature, what happens to melting point of ice? Increases or decreases, Andy? Melting point of ice decreases. If you increase the temperature, what happens to boiling point of water? Boiling point of water increases. If you increase the temperature, solubility of gas increases or decreases, Andy? Decreases. If you increase the pressure, solubility of gas increases. Okay. Solubility of solid depends on whether it is endothermic or exothermic. Solid in liquid, if it is endothermic, as temperature increases, solubility increases. If it is exothermic, as temperature increases, solubility decreases. And finally, I am giving one example. 2N2 gas plus 3H2 gas, 2 moles of ammonia gas plus heat. It is an exothermic reaction. Now tell me what happens if you increase the concentration of N2 or concentration of H2. It proceeds in which direction, Andy? Forward direction. If you decrease concentration of ammonia, it proceeds in which direction? Forward direction. Okay. If you decrease concentration of ammonia, it proceeds in forward direction. If you increase concentration of ammonia, it proceeds in which direction? Backward direction. If you increase pressure, it proceeds in, on increasing pressure, it proceeds towards less number of moles. And less number of moles means product side, forward direction. On increasing pressure, it proceeds in forward direction. On increasing temperature, it proceeds in backward direction. Okay. If we add inert gas at constant volume, is there any effect or no effect, Andy? No effect, whatever may be the type of reaction. If you add inert gas at constant pressure, it proceeds backward direction towards more number of moles, that is backward direction. Tell me favorable conditions for formation of ammonia. Favorable conditions for formation of ammonia with respect to temperature and pressure. You tell me. With respect to temperature and pressure, high pressure, low temperature. High pressure and low temperature. If you increase pressure, it proceeds in forward direction, and if you decrease temperature, it proceeds in forward direction. So high pressure and low temperature. Okay, so in laboratory, if you are doing this reaction, so whatever the experimental conditions we have to follow, high pressure and low temperature we have to follow to get more yield of ammonia. Okay, so that is the application of chemical equilibrium. What are the conditions to be maintained to get more yield of product, that we can know only. Right, this is the theory part we have from chemical equilibrium. Theory part completed. So we discuss some problems and take a break for 15 minutes.